In the last video, we learned that atoms can have a magnetic dipole moment, and materials can be viewed as a collection of atoms, so they can have a lot of small magnetic dipole moments. And we also introduced the magnetization, which is the magnetic moment per unit volume of the material. Now, in this video, we will discuss the field of a magnetized object. What is the magnetic field created by an object that has a magnetization? So consider an object with a certain volume and with a magnetization M like this, and with no electrical current running through the material. So we will show that an equivalent picture of this is to view this object as a volume with bond currents. The bond currents running on the inside have a volume current density J sub B equal to the curl of the magnetization, the curl of M, and the bond surface currents running on the outer surface of the material have a surface current density K sub B equal to M cross N hat. So first, we do the case of a uniform magnetization. If the magnetization is the same everywhere in the material, it means that all the small dipole moments have the same density, and we can represent the small dipole moments as small current loops in the material. Now, if you look on the inside, you can see that each time you have a little current in a certain direction, you will have another little current in the opposite direction right next to it. If these currents are equal, then they cancel each other, and you have no current inside the material. But on the edge of the material, all the little currents are in the same direction, and there is nothing to cancel them. So the result is that there is a surface current right on the edge of the material. Now, we will show that the bond surface current density is given by M cross N hat. For this, let's consider a small volume with the top area A and the thickness T. This volume has a uniform magnetization M, which can be understood as due to electrical currents running around the edge of the volume. The magnetization M is by definition the dipole moment per unit volume. The total dipole moment, which is a small m in the book notation, is therefore the integral of the magnetization over the volume. So integral of m d tau prime. Since the magnetization is uniform, I can write the total dipole moment as m times the volume, so m times at. But we also know that the total dipole moment can be calculated as the current I times the area of the loop A. So combining these relations, we find that I is equal to m times t. I is the total current, but the surface current density K is obtained by dividing by the thickness. So K equal I over T, and since I is equal to mt, then K is equal to m. So you see that the value of the surface current density is equal to the value of the magnetization. And finally, since Kb is a vector perpendicular to m and perpendicular to the normal of the surface, we can write vector Kb as m cross n hat. Now let's check something. You can see that there are no current on the top or bottom surface of the volume. This is consistent with this expression, since for the top or bottom surface, m is parallel to n hat. Now, a comment on the term bond current, right? Keep in mind that no charge actually makes a large ripple on the material. It's only tiny orbits in a single atom, and this is why we call this bond current, to distinguish it from the usual electrical current, where the charges are moving from atoms to atoms over larger distances. Now, we consider the case of non-uniform magnetization. We consider two blocks next to each other in the y direction. The blocks are small enough so that the magnetization is uniform through each block, but now the magnetization of each block is different. The one on the left has a magnetization along Z that is mz at position y, and the one on the right has a magnetization along z that is mz at y plus dy. Again, this magnetization can be understood as due to electrical current running around the edge of the volume. But this time, since the magnetization is not the same, the currents are not the same. And so inside the material, the currents will not cancel each other. You can see this here by looking at the current in between these two blocks. The left block contributes a current along minus x. The right block contributes a current along plus x. But since they are not the same, they do not cancel each other. And so there will be a current along x. Let's calculate what it is. So we just showed that the surface current density is equal to the magnetization, K equal M. If we want to calculate the total current, we need to integrate over the thickness of the block. So I is equal to K dz. And since K is equal to M, then I is equal to M dz. Now here we have two currents to add. So the current Ix is equal to mz at y plus dy minus mz at y times dz. Again, this is because we sum up the contribution from the two blocks. One is positive, the other one is negative. And because the magnetization is not uniform, the contributions don't cancel each other. Now, assuming dy is very small, you can recognize a derivative. Ix is equal to dmz over dy times dy, and then times dz. Now, dy dz is the area that is perpendicular to the x direction. So it is the area that is perpendicular to the current. And since the current density J is equal to di divided by dA perpendicular, then we obtain J along x is equal to dmz dy. And so once again, this is a bound current, so we write J sub B. Now let's look at the two blocks next to each other in a z direction. And let's assume that they have a magnetization along the y direction. The one on the bottom has a magnetization along y, that is my at position z, and the one on the top has a magnetization along y, that is my at z plus dz. Again, the magnetization can be understood as due to electrical currents running around the edge of the volumes. And again, the magnetization is not the same, so the currents are not the same. So again, on the inside, the currents will not cancel each other. And so there will be a current along x. And so again, let's calculate what it is. So again, we will use the surface current density, which is equal to the magnetization, so K equal M. And the currents are running perpendicular to a length dy, so I is equal to K dy, which is equal to M dz. So the current Ix is equal to minus M at z plus dz plus my at z times dy. And again, this is because we sum up the contribution from the two blocks. The top one is negative, the bottom one is positive, and because the magnetization is not uniform, the contributions don't cancel each other. So same as before, we write this as a derivative, assuming dz is very small. So Ix is equal to minus dmy over dz times dz times dy. dz dy is again the area perpendicular to the current Ix. And so this time we obtain that the bound current density, J sub B, is equal to minus dmy dz. So we found two contributions to the current density along x. One was dmz dy, and the second was minus dmy dz. Now, we won't do this again. For the current along the y direction, I will write the results. We find J sub B along y is equal to dmx dz minus dmz dx. And if we do this along z, we find J sub B along Z equal dmy dx minus dmx dy. And so overall, you recognize that we have a curl, right? J sub B is equal to the curl of M. So let's summarize. We showed that if you have a volume with a certain magnetization and no electrical current running through it, it can be viewed as having bond currents on the inside, and the volume bond current density J sub B is equal to the curl of M. And you have bond currents on a surface that have a surface bond current density K sub B, which is equal to M cross N hat. Now, a few lectures ago, we learned that the vector potential of a single magnetic dipole is given by mu naught over 4 pi times M cross curly R hat over curly R squared. Now, for material, we have a lot of atoms with a lot of magnetic dipole moments. So if we write the vector potential in terms of the magnetization, we integrate the expression over the volume. So A at R is equal to mu naught over 4 pi integral over the volume of the magnetization cross curly R hat over curly R squared, d tau prime. Now, based on what we just learned, we can calculate the vector potential another way. We can calculate the vector potential from the bond currents. A at R is equal to mu naught over 4 pi integral over the volume of J sub B over curly R d tau prime plus mu naught over 4 pi integral over the surface boundary of the material of K sub B over curly R dA prime. And of course, you can get the magnetic field from the curl of A or from the Biot-Savart law. So you can calculate the B field from the bond currents integrating over the volume with the volume bond current density J sub B and integrating over the boundary with the surface bond current density K sub B. So the bond currents gives you another method to calculate the vector potential and the magnetic field. Okay, before we conclude this video, let's do a couple questions. So a solid cylinder has uniform magnetization M throughout the volume in the x direction. What is the magnitude of the total magnetic dipole moment of the cylinder? All right, if you answered A, then you're correct. The magnetization is the dipole moment per unit volume. So to get the total dipole moment, you need to integrate over the volume. So here the magnetization is uniform. So you just need to multiply by the volume of the cylinder, which is pi r squared times L. Okay, next question. This time the solid cylinder has a uniform magnetization in the z direction. Where do bond currents show up? Okay, if you answer D, you're correct. The magnetization is uniform, so there is no volume bond current density, but there are surface bond currents. K sub B is given by M cross N hat, so they are perpendicular to M and perpendicular to N hat. On the top and bottom surface, M and N hat are parallel or anti-parallel, so there is no surface bond current on the top and bottom surface. But on the side, on the rounded surface, yes, there are surface bond current. Now, next question. This time, the solid cylinder has a uniform magnetization in the x direction. Where do bond currents show up? If you answer D, you are correct. Again, the magnetization is uniform, so there is no volume bound current density, but there are surface bound currents. K sub B is given by M cross N hat. On the top and bottom surface, M and N hat are perpendicular, so there are surface bound currents. On the side rounded surface, there are plenty of regions where M and N hat are not parallel, so there are surface bound currents there too. On the left side or on the right side of the rounded surface, then M and N hat are parallel, and so there are no surface bound currents there. Next question. This time the solid cylinder has a magnetization in the phi direction. In which direction does the bound surface current flow on the curved side? All right, if you answer D, you're correct. Again, you need to do a cross product to find the direction. M cross N hat gives you the minus Z direction. Okay, last question. A sphere has a uniform magnetization M throughout the volume in the Z direction. So which formula is correct for the surface current? All right, if you answered B, you're correct. First, you find the direction that is perpendicular to M and perpendicular to N hat, and it is phi hat. Then the cross product is M cross N hat. So magnitude of M times magnitude of N hat, which is 1, times the sine of the angle between M and N hat. So this angle is theta, the polar angle in spherical coordinates. So M sine theta along phi hat. Okay, that's it for this video. See you soon.